In this video, we're going to discuss some of the logistics of the number of edges and how that can relate to the number of nodes. We're going to begin with what's called a complete graph. This is, in a sense, an upper bound on the size of a graph. So a complete graph is a simple graph with an edge between each pair of nodes. There's a notation for it. We really won't use that in this class, but I included it here in case you wanted it. So it's k with a subscript. Let's say we looked at k5. That is the complete graph that has 5 vertices. So we need to draw in 5 vertices. 1, 2, 3, 4, 5. And then every single pair of vertices is connected. So this vertex over here, let's call it V1. Then this one V2, this V3, this V4, and this V5. I need to draw an edge from V1 to V5 to V4 to V3 and to V2. From V2, I need to draw an edge to V1 and then V5 and then V4 and then V3. From V3, I need to draw an edge to V2, to V1, to V4, and to V5. From V4, I need to draw an edge to V5. And I've accidentally drawn sort of a pentagram here. Hopefully that doesn't cause any problems. And if we look at this, let's find out how many edges this has. Well, for the first one, I drew an edge 1, 2, 3, 4 edges I drew. For the next one, I drew 1, 2, 3 edges. The one after that, I drew 1, 2 edges, then, 1 edge. Notice that every single time we start an edge and draw all vertices from it, the next vertex that we go to, we will not need to draw one edge because we will not have to draw an edge backwards. Therefore, if I had to draw n vertices at the first node, I would need to draw n minus 1, and then n minus 2, and so on. However, we do need to be a bit careful here. So this isn't actually what we want. What we want is the first one, when we had 5 vertices, we drew n minus 1. We drew to all other nodes. So we start with n minus 1 plus n minus 2 plus n minus 3, and we go all the way down until 2 and then to 1. And we've seen that exact arithmetic sum about 49,000 times in this class. So we hopefully know that that converges to n minus 1 times n all over 2. Therefore, let's write this. This is n squared over 2 minus n. That is an upper bound, in some sense, on the number of vertices that we could have in a graph. We'll keep that in our minds when we are trying to compare different runtimes. So earlier, for example, we saw that the number of edges times 2 was the amount of data stored for a adjacency list. And if I know this is bounded above by this expression that I had over here, where n is the number of vertices, this is less than or equal to 2 times v squared over 2 minus v. So this is less than or equal to v squared minus 2v. Therefore, no matter what, the adjacency list was less than the adjacency matrix because v squared was the size for the adjacency matrix and we are subtracting something from that. This is a useful idea to have. The adjacency matrix will always take more data, but may be more useful for certain properties. Our next thing we want to talk about is what's called the handshaking lemma. This is the sum of the degrees of the vertices of a graph must be even. I'll include a typeset proof for you guys if you want to see that, but the idea here, mostly, that we need to know is whenever I have two vertices and they are connected by an edge E, if this is vertex U and this is vertex V, if I'm counting the total degree, this edge will get counted both for the degree of U and for the degree of V. Therefore, every single edge is counted twice. So it actually turns out that the sum from I equals 1 to n, if n is the number of vertices, and m is the number of edges, if I add up the degree, deg, of each vertex vi, then this is exactly equal to twice times the number of edges, because every edge is counted twice. I will include a formal proof of this in your version of the notes to look at, but here I wanted to just show you how we can do this. We'll use this fact many times in this class as a useful way to understand if we need to process every single vertex. In a sense, how long does that take? Because frequently we will need to look at every single vertex from every single node, and that is what we are thinking about here. If we are checking every single vertex from every single node, this sort of thing may show up for us.